let's try to solve this question here. So there are 5,620 lines per centimeter in a grating that is used with light whose wavelength is 471 nanometer. Okay, so let's sketch the situation here. So it's a diffraction grating that we're talking about. Because they're talking about grating, then they say there's 5,620 lines in each cm of the diffraction grating. So I represent diffraction grating by a series of dots to represent that there's a lot of slits in it. Okay, so they say that you can find around 5,620 lines per cm. So per cm. Okay, so the wavelength that you're going to send to pass through this diffraction grating, the wavelength, it's 471 nanometer. Okay, a flat observation screen is located at a distance of 0.74 meter from the grating. So we are going to place a screen at a distance of 0.740 away from the diffraction grating. And this center line is just to indicate where's the center maxima later. But generally the idea is the distance, it's 0.740 meter. Okay. What is the minimum width that the screen must have? So this is the screen. Then they say what is the minimum width? So the minimum width to have what? The minimum width so that the center of all the principal maxima form on either side of the center maximum fall on the screen. So they want all the principal maxima, their center to be on the screen. So if there are 7 maxima that can be found for this diffraction grating, what's the minimum width that you need to have in order to fit in that all 7 maxima in that screen? Okay, they are focusing on the center of the maxima. So because maxima technically there's a bit of a width to it. Okay, there's a bit of a width to the maxima because that's how diffraction happens. So they are only focusing on wanting to get the center of each maxima to fit onto the screen. So if they want to fit all the maxima on the screen, what is the minimum width required? So when they say the width of the minimum width of the screen, this is the width of the screen that we are talking about. So I will label it as width of the screen. Maybe if you want to add on the word minimum, that's fine as well. Okay, so that the center of all the maxima can form on the screen. So we need to know how many maxima are there first. Then once we know how many maxima are there, we can deduce what is the width that we need. Okay, so to know how many maxima we have, we need to determine what is the maximum order that can be fitted in for this diffraction grating. We know that for diffraction grating, d sine theta is equals to m lambda. This is diffraction grating. So we want to determine our d first. So d can be obtained using an inverse of n. Okay, we know that our n is 5,620 lines per cm. So this is the part you need to be careful about. It's per cm, so it's cm -1 below. Okay, so because you put cm -1 at the denominator of this fraction, once you bring it up to the side or you bring it upwards to the numerator, basically this -1 will disappear. So you get 1 over 5,620 cm. Okay, we know that we want our d to be in the SI unit, so we need to convert it from cm to meter. So another conversion, so 5620 cm, you want to eliminate cm and introduce meter instead. So you know that in 1 meter there's 100 cm in it. So you can proceed to convert it to become 562000, okay, per meter. Okay, this is not per meter, sorry. Okay, your m is at the numerator, so you cancel out the cm, so your m will stay as the numerator, so the unit is meter. and D here is the distance between adjacent slits. Okay, from one slit to the next slit, what's the distance between them? So since it's a measurement of distance, it's reasonable that the unit is in meter. Okay, so 1/56200 okay, sine theta is equals to m lambda. So this is the situation that we have right now. So let's try to think. We want to know how many maxima can we find on this screen over here. So we need to know what's the maximum m you can achieve. You know that m equals to 0 start at the center, then further ahead you have m1, m is equals to 2, m is equals to 3, so on and so forth. But you want to know what is the maximum m that can be achieved. Okay, you know that as you go further and further away from the center maxima, your angle will be increasing. Okay, so let me just draw here a rough idea of the situation. So let's say this is your center maxima. Then at some point further, you find your first maxima. Then at some point even further, you find your second maxima. And at some point further, you find your third maxima. Okay, but the general idea is when you go from 0 to 1 to 2 to 3, the angle that you find here, the theta over here, will be larger and larger. But no matter what, you can deduce that the angle, no matter how far it gets, it should never exceed 90 degrees. Because if you start from here, you go up to 90 degrees, 90 degrees will be exactly vertically upwards already. So if your light diffracts to the level that is vertically upwards, technically that light will move upwards and you never arrive at the screen anymore. So if you want your maxima to be formed on the screen, the angle that you can go to can only reach to a maximum of 90 degrees. Once you reach 90 degrees, right, that maxima can never be formed on the screen because your screen is at somewhere on the right hand side. So if you want that maxima to be arriving at the screen, you must have an angle that is less than 90 degrees. Or in other words, the maximum angle that can be spanned will be from 0 degree until 90 degree for our diffraction pattern. So the maximum theta that we can have is 90 degree. So if we know that the maximum is 90 degree, we can deduce what is the maximum order that we can have. So the idea would be, okay, maybe I'll remove this line first. I'll manipulate the equation first. Okay, I'll say that D sine 90 is the maximum possible amount that you can get on the left hand side. Okay, on the left hand side, the maximum you can get is D sine 90. So no matter what, your m lambda has to be less than this D sine 90. Okay, it has to be 80 something or 7 something or 60 something, but it can never reach 90 degree. So in that case, your m here, your m lambda here must be less than D sine 90. So you can say that D sine 90 is greater than m lambda, or m lambda is less than D sine 90. Okay, so from here we can also write things more clearly and say that since this is m, we can call it the maximum m, or we label it as m max. Okay, so this one is m max. Okay, so done. So we can find right now, we can try to determine m max by doing a substitution. Okay, so 1/562,000 sine 90 degree is greater than m max, which we want to determine, and the wavelength that we are using is 471 nanometer. Okay, so through this calculation, you find that m max must always be less than a value which is 3.778. Okay, and you already obtained m max is less than 3.778, and you know for a fact that since m max must be an integer, right? M max can only go from 0, 1, 2, 3, 4, 5, nothing in between. There's no decimal place for m max over here. It must be an integer. Since m max must be an integer, we know that the integer that is smaller than 3.778, but the nearest to 3.778 will be 3, right? Okay, it can never exceed 3.778. So even though 4 is nearer, you can never take 4 because we are still less than 3.77. So the nearest integer we can put is 3. So we can say that m max is equals to 3. Okay, so this is exactly matching what I'm drawing here. You can have 0, 1, 2, 3, but your 4 will be outside of your range, so you can never draw a fourth maxima over here. The fourth maxima can never be formed on the screen because yeah, it's not within the angle of 0 to 90 degree over here. Okay, so now you know that mx is equal to 3. You can now try to determine this angle over here. Okay, you can find this angle over here to know for exact what's the angle over here. Right now we know that it's less than 90, but we still don't know for exact what is this theta 3 over here. So that's probably our next step. Okay, so we can see that d sine theta 3 is equals to 3 lambda. Okay, we find theta 3 right now. So it's still the same d, so this is 562,000 sine theta 3 is equals to 3 times lambda. So lambda is 471 times 10 to the power negative 9. So from here you can find theta 3 has an angle of 52.57. Okay, so this is theta 3, the angle that you can go from the central maxima to the third order bright maxima on the left hand side, on the upside or the downside. What am I saying? On the upper side or the lower side. Okay, so this is theta 3 over here. Now we need to use this theta 3 over here to obtain information about our width of the screen. And we know that we can split the width of the screen into two parts. Okay, let's split it into two parts. Break it in the middle. Then you can see that what you have here is actually a triangle, right? You can see it's a triangle over here, a right angle triangle. So if you see this is a right angle triangle, you can see that we have our angle theta, and we have the distance between the slit and the screen as our adjacent, and we can have half of the width of the screen minimum as our opposite. Okay, so from here we can probably build an equation based on trigonometry to find the width of the screen, the minimum width of the screen. So we know that tangent theta 3 is equals to the opposite, which is half minimum width of screen. Let's write W minimum. Okay, divide by the adjacent, which is D. Okay, so we can do our substitution. Tangent, the theta 3 is 52.57 divide by, okay, you have half above, you have width of your screen minimum above, and your distance is 0.740. Okay, so if you substitute everything inside, okay, this is half the width of the minimum width of the screen. So you substitute everything inside, you get the width, the minimum width, to be equals to 1.93 meter. Okay, why is it half the minimum width? It's because your center of the central maxima splits the screen into the upper half and the lower half, and since they are symmetrical, the upper half should have the same width as the lower half. So if you are just able to find the upper half and you times it by 2, you are getting the whole width of the screen. Okay, and why is this the minimum width of the screen? It's because if you extend it further, it's fine as well. If you extend it further, you can still form the third order bright maxima on the screen, but you're not getting any more than that. Okay, that's the furthest maxima that you can go. Even if you extend the screen further up to infinity, you are still going to get the same 3 maxima that you see here. Okay, that's why we call this a minimum width of a screen, because you cannot go less than that. If you go less than that, then the third bright maxima here cannot be formed, because the light will basically fall away or above the screen already. Okay, so the maxima can never be formed if your width of the screen is less than that. Okay, so another thing I would like to point out, which is not asked in the question, is what is the number of bright maxima that can be observed on the screen? Okay, you know that the maximum order is 3, but that is equivalent to how many bright maxima actually? Okay, so to visualize it, I'm going to fill in the lower half as well. So lower half is going to have its first order bright maxima, the second order bright maxima, followed by the third order bright maxima. Okay, so there's -1, -2, and -3. and this completes the whole picture. So if you count it one by one, you get 1, 2, 3, 4, 5, 6, 7. So there are 7 bright maxima that can be observed. But actually, if you think about it, it's taking the maximum order, which is 3, multiply by 2, because that's both sides of the central maxima, so you need to multiply by 2 to get 6 bright maxima, and you have to add on by 1 in order to account for the central maxima that you can see here. So if you're interested to determine what's the number of maxima observed, okay, the number of maxima observed can be determined by taking m maximum, take your m maximum, multiply by 2 because you want to take into account both sides of the screen, and add on 1 to take into account of the central bright. Okay, so this is 2 times 3 plus 1, so in total you are able to get 7 maxima on the screen over here. Okay, so 2m plus 1 here is also an important skill to have in order for you to determine how many maxima you can form on the screen. Okay, so this is an interesting question because even though they start off with an equation that you are used to for diffraction grating, but it requires some knowledge of trigonometry in order to solve the problem correctly. Okay, so I think this is an interesting question that you should definitely try to be very familiar with the idea of how to manipulate between the angles and the distance of the slit and screen, and also the separation y over here. Okay, so that's it for this question. Thank you very much.